All right, good afternoon. This is Jason Thomas. I'm a project engineer and portfolio coordinator here at America Makes, and I'll be your host for today's America Makes TRX webinar series. Little background on the TRX webinar series before I introduce our speakers. As America Makes continues its mission to expand and accelerate the footprint of additive manufacturing and 3D printing, this medium called the America Makes Technical Review and Exchange webinar series was created. By creating this platform, it allows the additive manufacturing and 3D printing community to come together and share knowledge and experience with a much broader community. If you or your team are interested in presenting during a TRX webinar series, um, you can complete the request form on our website, or you can reach out to myself, Jason Thomas, directly. A few important notes before we kick off the series. There will be a brief Q&A period at the end of today's presentation. Please enter your questions in the chat, and I will ask them during Q&A. I'll do my best to get all of your questions answered. Today's webinar is going to be on unlocking velocity and metal AM materials development through testing. Without further ado, it is my pleasure to introduce Ed Herderick, David Scanapico, and Calvin Stewart from NSL Analytical. Ed Herderick is the Vice President for Science and Technology Development at NSL Analytical. His responsibilities include architecture and qualification, testing, and analytical measurement solutions with customers in industries ranging from additive manufacturing to hypersonics to batteries and beyond. He is also the Special Materials Science Executive for May River Capital. His passion is industrializing and commercializing transformational materials technologies for high consequence applications. Prior to joining NSL, he was the Director of Additive Manufacturing at the Ohio State University Center for Design and Manufacturing Excellence, CDME. He was responsible for all additive activities supporting CDME's mission to provide industrial education to students, user facilities for faculty and partners, and bringing manufacturing innovation to Ohio industry. Ed has also held leadership roles at GE, RP&M, and EWI. Right. David S. Scanapico is the Scientific Development Manager at NSL Analytical. His responsibilities include researching, developing, and teaching materials characterization techniques, materials testing, and analytical analysis to support customers across industry and academia. David recently graduated from Case Western Reserve University, where he conducted alloy development research with NASA Glenn Research Center. He has a passion for discovering and developing advanced analytical techniques to overcome characterization obstacles. Calvin M. Stewart is the College of Engineering Innovation Scholar and Associate Professor in the Department of Aerospace and Mechanical Engineering and Department of Materials Science and Engineering at The Ohio State University. He obtained his bachelor's, master's, and PhD in mechanical engineering at the University of Central Florida in 2008, 2009, and 2013, respectively. Dr. Stewart directs Materials at Extremes, which focuses on the advanced manufacturing, mechanical testing, and theoretical mechanics of materials subject to thermal, mechanical, and chemical extremes. Ed, David, and Calvin, I'll now turn it over to you and your team. Go ahead and take it away.
Thanks, Jason. Can you hear me okay?
Sure can.
Okay, great. And David, I'll just let you know next slide. So again, good afternoon, everyone. This is Ed Herderick here. I tried turning my video on, but it slowed way down with the number of attendees we had. So anyhow, thanks so much for being here. The goal here, I'll walk through the outline, is we're going to present for about the next 45, maybe 50 minutes, and have plenty of time at the end for a nice dialogue. So if you have questions, we look forward to those during the Q&A. You're welcome to drop them in the chat, or maybe if you raise your hand, we can address those. Next slide, please, David. So thank you for the kind introduction, Jason. Just to put name with the face here. Again, that's me talking in the top left, Ed Herderick, David Scanapico, and my former colleague and now collaborator, Calvin Stewart, who's going to be talking about materials at the extremes at Ohio State University. Next slide, David. For those of you who don't know NSL, we're a Cleveland-based company focused on testing and characterization of materials. We have 2 sites in the greater Cleveland area. We do a whole range of different testing technologies, a number of which support additive manufacturing. So I just have a list here. I won't read you through the whole list, but you can see the different things we do, and David's going to go through a number of our different techniques later on in the presentation. Next slide, please. A high-level outline. So I'm going to kick us off by talking about Moore's Law, which is the exponential technology development curve that Gordon Moore coined in 1965 for semiconductors, and draw some analogies to our current state of development in metal additive manufacturing. Then I'm going to turn it over to David, who's going to talk about the current state of industrial metal testing for additive manufacturing. And then Calvin will cover the third section, talking about his research at Ohio State in the Materials at Extremes MatX lab. And then I'll close with a quick overview slide to seed some of the discussion with the heading, what do we need to keep going and keep developing new materials for additive manufacturing? Next slide, please. So again, I just have 3 slides here. I'll turn it over to David then. I mentioned Moore's Law. So this is the curve from Gordon Moore's original article that he published back in 1965, cramming more components onto integrated circuits. So Moore's Law says a doubling of the number of transistors every 2 years. So if you think about that in power 10, that's about a 10-fold improvement every 7 years. And a lot of our modern life has been driven by Moore's Law. There's also other related developments. Jensen Huang at NVIDIA talks about GPU power per chip. And part of what I want to introduce here and have been talking about on the speaking circuit all summer and this fall is how this relates to additive manufacturing. Next slide, please. So there's a lot of different elements to this. I'm going to highlight 3 here on this slide and then a 4th on the next slide. And I think this is the foundation by which we're seeing all these new applications come out in metal printing, moving from prototyping to production. So the first one that I think is really exciting as an interesting corollary to Moore's Law is the cost of metal printing is coming way, way down. I just have highlighted there Exact Metal, who's been a collaborator of mine for many years. And now they have in this very cost-effective segment of laser powder bed fusion, a really nice set of equipment that they're selling that's in the low 6 figures. So an interesting new dimension to the market that didn't exist previously. Another one that's driving a lot of development is advancing wire-based printing. So I have an image there from Lincoln Electric Additive Solutions here in the greater Cleveland area. So they're on the end of the spectrum in terms of very, very high productivity, right? They're measuring their productivity in pounds per hour, and they measure their parts in not just centimeters, but in meters cubed. A really exciting entrant into the metal printing space. And then another one would be binder jetting. So 3 different modalities here on this page. Binder jetting really is developing a niche on the metal side in high volume production because of its ability to scale with MIM processing. Next slide, please. And then what I did on this slide was charting at a high level. Happy to talk about more data, happy to talk with folks offline, is just a sort of snapshot historical view of productivity in centimeters cubed per hour for laser powder bed fusion of metals. And what I think is really exciting about this curve is mapping it out is we as a community, the royal we, have gone through a 10,000-fold improvement over roughly 30 years. So at least for this chart, and I think if we chart it out for the cost out, for the productivity on the wire-based side, for the binder jetting as well, we are tracking Moore's Law for metal printing, which I think is really, really exciting. And I'll just highlight here. So the 3 chapters that I've broken out are sort of the early metal printing feasibility. So this was low power lasers, low density, very low productivity, less than 1 centimeter cubed per hour for sure, maybe even just a few per day, up to the first laser powder bed machines that weren't doing fully dense metal. And then in 2004, that's really when the fiber lasers came out, 200-watt fiber lasers integrated into these machines, that companies were first able to demonstrate fully dense metal with the single Gaussian laser. That was sort of perfected. There have been a lot of interesting developments and a lot of TRL, MRL maturation for parts. And then I have this demarcation line at about 2014 when a lot of the industrial multi-laser systems were introduced. So that's that next star there at 2014. And now we're into the hundreds or even potentially up to 1,000 cc's per hour for metal laser powder bed fusion with multiple lasers, splitting beams, jumping around, dynamic focus ring lasers. There's been so much development in the space. It's really, really exciting. And I start with this as the frame for the testing conversation because there's been so much development on the process side that now it's opened up this whole opportunity for developing new materials and new applications for metal printing. And so at NSL and also at Calvin's lab, that's really what we're thinking about, is how to support the qualification and certification of all of the new parts and new materials that this exponential productivity has entitled in an engineering sense to the market. So David, I'll turn it over to you for the next section of the presentation.
That was great. And I'm gonna give my camera a try. We'll see if this works out. If it doesn't, I'll turn it back off. But hi, my name is David Scanapico. I am the Scientific Development Manager here at NSL. So I'm going to go through my expertise is in alloy development. So everything from atom to mechanical properties is what I study and where I consider my interest to lie. So when we look at additive manufacturing, there are quite a few unique situations and instances for this process that we need to characterize before we can get to a point of qualifying these for manufacturing, especially in the case of aerospace or space, where the needs are very, very precise. So if we look at NIST, and they've identified three major challenges for approaching qualification of additive manufacturing. First is largely just the complexity of the parts. The freedom to design whatever we want in additive space. It also introduces a challenge of how can we even test things like lattice structures, which you could see up in the top right there, where the struts of that lattice are hundreds of microns, if that. Where can we get mechanical data that's reliable, that can produce the performance of that part in its application? Similarly, you get internal structures where you're going to get the as-built surface of additive manufacturing, which has a known severe impact on fatigue properties, stress rupture properties, etc. So that's a major concern of how do we characterize those and how do we approach qualifying those? Not to mention reaching internal structures from an inspection point of view is a challenge. I'm not going to go through internal defects. It's a pretty common piece of additive manufacturing, and I think that it's covered mostly by everything else. But when we get down to microstructural deviations, we have largely not so well understood residual stresses that appear in our parts as we're manufacturing them, especially comparing machine to machine. Not all AM machines are created equal, and not all AM techniques produce the same parts. Then you get into unintentional or intentional chemical gradients, right? With this ability to produce whatever we want from a design freedom perspective. How do we test, say we do a gradient property material? How do we make sure that those gradients are accurate? Do we need to do 10 chemistry tests? Do we need to do 10 tensile tests for one part? I mean, it's a tenfold increase, right? And so there's a lot of opportunity there to figure out the best way to approach those components. And then finally, metastable phases. I don't need to go into too much detail that additive is not an equilibrium-based process. And so you're going to get phases that we're not expecting or that are extremely deleterious to a part's performance. And how do we manage the expectation of those, as well as if we can't get rid of them very easily? So I'll step through a couple of solutions that exist in literature at the moment, but mostly this is to open up a conversation between testing labs, research groups, and manufacturers and industry so that we can optimize the testing process to qualify those AM parts. I mean, this is an ongoing conversation. There's no silver bullet here today. But so in some cases, we've found correlations between micro testing and your typical ASTM standards. You can see great agreement in this miniature tensile test specimen here as compared to the round standard bar of 6 millimeters in diameter. And when we go forward with that, right, I can make this tiny specimen that I can now carve out of a complex shape like this turbine in multiple different ways. We've got horizontal bars, we've got vertical bars. They're coming right out of the fins, so we know the properties of the fins in the radial direction, which is exactly what the application is going to perform at. And you can see, compared to two other literature sources that compare the Inconel 718 properties here, our miniature tensile specimens are performing on par, which is a great discovery, so that we can look at, all right, we have complex shapes, but now we can test them no matter, well, not no matter, but even if they get very thin walled or very small component wise. When we look at getting into the microstructural deviations, right, I think the golden standard is always to go back to forging. You get a single heat of material, a largely homogeneous ingot of whatever material you're working with. It's forged and heat treated in groups together so that when you get to the end, the predictability between the microstructure of all those pieces is extremely accurate, extremely precise. So the testing requirements are not very severe, 1-2 components at most per batch, and that certifies tens to hundreds of sample or of parts depending on the quantity and the quality of the size. So in additive manufacturing, how can we get to that level, and what are the challenges that we find when we're trying to approach this? So the key here, one of the major differences is that obviously additive manufacturing is not a solid state process. In forging, you've cast your ingot of metal and then it never melts again until it's in application, and hopefully never melts in application either. But in additive manufacturing, we're remelting several times within the process. And yes, we're working in an inert atmosphere, but even at 0.1% oxygen partial pressure in the chamber, which is where a lot of additive manufacturing machines will start printing at, you end up with oxides in the material because liquid metal loves oxygen. And even worse in some cases, the unintentional chemical gradient part, we superheat the metal. So it's not just getting it into a molten state, but it's superheating it, and in many cases vaporizing it. And you see that on the inside of additive manufacturing machines, you get coats of whatever metal you're working with on an atomistic level, but it does exist. And that can make some uncertain chemical changes from our powder stock to our final product. And understanding all of these changes and how adjustments of the additive manufacturing parameters play in these cases, it needs to be well understood. In addition, when you're building your component, your grain size changes from the bottom to the top of the build. And so, compared to forging, the microstructures of a single print of parts is not uniform. And how to go about treating all those parts, whether you treat them as equals or not, is a major question. Yep. And here we go. How do we test those batch sizes? Do we need witness samples in every single build, which is a practical approach to the task at hand? But at the same time, if you're only building a handful of parts depending on the size of the build and the size of the part and the optimization of the packing of those parts, you could be looking at several-fold increase in testing requirements to certify the same number of components as, again, golden standard of forging, right? And so somehow identifying where the critical points of failure in each build setup could help us reduce the amount of testing significantly so that we can qualify these builds in a more effective manner. It's, again, it needs to be a conversation between test houses like NSL, research groups like Calvin Stewart at OSU, and the manufacturers to make sure that we're hitting everything we need to do to qualify these materials and advance out of the manufacturing into the industrial space. And finally, one of the major differences for additive manufacturing is your feedstock characterization, right? You have powders, not ingots. Surface area is much higher, much easier to collect oxygen and expire the powder, right? It can go bad over time if it's not being used. In addition, when you put the powder through a build, that chemical formula might change somewhat. And in those cases, we need to be able to certify that recycled powder is going to be as effective as virgin powder. So again, this is a question of, do we need to chemical test after every build or after every 5 builds or 10 builds? And you can see where there's an exponential increase in now chemical testing requirements, because not only do we have to certify batches coming out of powder manufacturers, but everyone in industry who's recycling powder is also sending for more chemical tests. And every existing powder lot is getting chemical tested over and over again. And it's unwieldy if you just look 5 or 10 years in the future. So how these parameters all play and what needs to be done in order to ensure that we're able to accurately make the parts that we need to, again, is a major conversation that needs to occur and is occurring. So I talk about the importance of testing the chemical makeup of the powder to make sure that it can be reused in the right way. And that's mostly because even trace impurities in powders can cause a significant change to the processing parameters. So in this case, you have a 304 stainless steel, and with just an addition of 160 ppm of sulfur, you change the convexity of the liquid metal in the weld pool. And that goes from being a deep penetrating weld, which is a more ideal in an additive case, to a shallow wide weld, which reduces remelting, potentially prevents layers from coming together, fusing the layers together. And so now your powder might change how it's able to be processed without you changing parameters to compensate for it. You end up with bad parts after some amount of time. Who knows how long it might take to absorb 160 ppm of sulfur. Similarly, for one of the examples, GRCOP 84, which is a copper chrome niobium alloy, if it has just 200 ppm of iron, its conductivity reduces by 10%. This is for an alloy designed for its conductivity in combustion chambers, this is a huge impact. And so much so that NASA regulates that the GRCOP has to have less than 60 ppm of iron in it. And you might think iron is not that hard of an impurity to get in your material. A lot of our tooling, both in additive manufacturing and the powder industry, is made of steels. And so collecting just 200 ppm of iron is very easy to do. And verifying that our materials are consistently not having these impurities is critical for both the performance and the processing of additively manufactured components. So again, some things that we can do, NSL itself has the capabilities of down to parts per billion if needed. In the parts per million range is much easier for us, but no doubt that we can detect these trace impurities. It's just how can we make sure that they're not coming in, and how much do we need to re-verify that they are or are not present. In addition, we can combine analysis techniques such as using phase extractions and XRD to detect those trace impurities, but at a more reasonable level and with a better eye for detail. So one thing that we did in my research, which again is GR-COP, this time we're working with 42, 4 atomic percent chrome, 2 atomic percent niobium. If you conduct XRD on the bulk material, which is this blue dashed line on the bottom here, you only see the copper peaks. There's not quite enough chrome to niobium dispersoids to identify using just XRD alone. But if we take some nitric acid, dissolve out the copper, and all you're left with is the untouched chrome and niobium dispersoids, and then you can XRD that as a powder, you're looking at far more detail. In just 6% of the alloy, we're able to detect far more detail using the exact same technique with just an additional step. So these are the kind of developments that we can find, particularly in new alloys as we approach for additive manufacturing. That again is a major conversation between test houses, research groups, and industry. And I think this is handing off to Kelvin at this time.
All right. So to continue our conversation, let me introduce my research group, which is Materials at Extremes. We're a group that focuses on advanced manufacturing, developing advanced non-standard test methods and characterization techniques, as well as theoretical models to help us understand the mechanics of materials in extreme environments. I've been at Ohio State for 1 year and been building a lab, basically building a testing theater focused on non-standard tests for AM materials. The next slide. So our group, in terms of advanced manufacturing, we're focusing on additive, collaborating with the Center for Design and Manufacturing Excellence at OSU, doing EBM, SLM, doing DED, basically exploring all of the different AM manufacturing techniques. And then within my group, we do the advanced testing. So we've developed this incredible extreme testing lab that allows us to try to replicate the environment, service-like conditions within real parts, as well as helps us to kind of accelerate the materials discovery process. And then with that testing data, we're able to create theoretical models, whether it's classical or whether it's using machine learning, to try to understand the behavior of materials and maybe even close the loop from process all the way to performance. Next slide. So this is an image of the lab that I've been building. It's kind of like a testing theater. I've got it lit up nice, but it basically is a suite of mechanical test frames that are set up with different types of furnaces, so we can test materials at extreme temperatures. We got a load capacity from 50 to 500 kilonewtons, so we can test a big steel beam if you want, or a small test sample. We've got different types of furnaces, from resistance heaters to induction heaters, that allow us to, melt materials if we aren't careful, as well as we have some pretty high heating rates. And then we use things like high temperature digital image correlation to enable some of our non-standard tests. Next slide. So before I get into the tests, the future concepts I have for testing, I want to touch a little bit of like the motivation for my research group. One of the motivations is the Materials Genome Initiative. We see it every day. We see it almost every other week. There's a company that comes out with a new designer powder, or there's a new AM technique or technology that's been patented. And there's a need for developing the process to create parts using those new technologies, or there's a need to actually figure out the processing parameters for a new powder. The White House put together a technology council, and they talked about this need to develop designer materials that are born ready, that we can manufacture at kilogram scales. And there's a lot of push, as Ed shown, trying to push the trajectory of AM, being able to generate these kilogram scale type of components. But the problem and the challenge is of all of these candidate materials and these candidate AM technologies, how do we qualify parts, the performance of parts, and verify that those parts are actually of a good quality? Click once. So my group is focused on kind of intersecting in this process. Before we get to the very expensive NASA, ASTM, AM qualification requirements, can we introduce advanced screening tests? Tests that allow us to just decide very quickly, we need to change our process parameters, or hey, we need to adjust the chemistry on this powder. So that's what we're going to talk a lot about today. Next slide. Another main motivation in my group, and something that we're building demonstrators with, is this idea of multi-metal components. There's tons of advantage we know about additive in terms of complex geometries and unique features, internal cooling channels and such. But something that has really started to come online in the last few years is this idea of being able to print multiple different alloys in the same build process, or even in an interrupted fashion, so that you can create parts that have spatial material design, not just geometric design, but spatially designing and placing material where you need it. So you can think of things like, well, we need a region that has high strength. There's a region that might need more cracking initiation, another region that might need more crack propagation resistance. There could be sections where we need tribology resistance, we need wear resistance. There's zones that need better heat transfer, or we want to save weight or costs. So something we're really interested in is this idea of gradient materials, or even materials that have kind of very defined boundaries that enable unique capabilities by material properties. Next slide. Now, for testing, we tend to do the basic conventional testing when it comes to AM. We'll do hardness tests on a cube, we'll do tension tests on a sample, we'll try to optimize from there. But me, I come from the high temperature realm. I don't, room temperature is nice, but I want to know how material is going to behave at elevated temperature. I want to do hot tension. I want to look at high temperature fatigue. And what my research group does a lot is high temperature creep of materials. Parts that have to last for years. What is the creep resistance of those materials? And the problem is that the ASTM standard test is a real-time test. If you want to know 5 years of creep data, you got to do a 5-year-long creep test. And every sample that you print, that's one test. So the costs and the timeline for high temperature, long-lived AM components is extremely long. Next slide. Now, in the AM, the official NASA, ASTM, SAE, AM qualification standards, there's 3 steps. There's installation qualification, where you install your machine, you calibrate it, you say, okay, it's qualified in place. Then there's operational qualification, where you load your powder and you print probably 6 build plates of lines, cubes, and specimen to verify that you can get consistent properties with that powder on that specific machine. And then you go to performance qualification, where you start print parts, you do NDE, and you print witness samples. This chain of qualification is extremely expensive and time consuming. And when we think about even materials discovery, the Materials Genome Initiative, we're trying to create new powders rapidly. It really is not feasible for us to use conventional tests that could take years if it's creep in order to understand the performance of materials. So there's a need for new test standards, new methods, things that are outside of the box, so that testing and qualification can keep track and speed with the AM technologies and materials that are coming out every week. Next slide. So the future concepts that I'm going to present today are going to cover a couple of different areas. In my opinion, I think the future concepts are to develop rapid tests that accelerate our ability to get information in a shorter period of time, create tests that are parallelized, that allow us to get more than one data point per specimen per test. And then finally, tests that are miniaturized. How can we reduce the volume of material that we need to print the volume of powder that we use to get operational qualification or witness samples and specimen when we're doing performance qualification. Next slide. So we're going to go into rapid, and I'll discuss some of the work that my team has already done, and we're going to focus in on creep because that's an area of interest in my group. So one of the non-standard tests that we've developed is a test called the stepped isostress method. In a conventional creep test, you hold stress constant or a constant load, constant temperature, and you wait. You wait until it fails. It could fail in a month, it could fail in a year, it could fail in 10 years, depending on the combination of stress and temperature. And when that specimen fails, you have one data point, one curve that gives you information about how that material performs. And that's only at that stress and temperature. Now, if you want to know the span of service conditions, well, you need to do multiple tests at multiple combinations of stress and temperature in a basement somewhere and wait many years to get your data. With stepped isostress method, instead of doing that, we hold temperature constant and we dynamically increase the load to create a test that will fail sooner, dynamically changing. We design our test matrix based on deformation mechanism maps, time temperature transformation, precipitation, to try to nucleate at minimum the presence of the right phases and precipitates. And by doing this process, using a well-posed model, we're able to predict the conventional response of the material. We're actually able to extract multiple curves of creep information from a single test. Next slide. So this is an example. This is a paper that we published in ASTM's Material Processing and Characterization Journal, where we studied some wrought Inconel 718. We age hardened it. We found the mechanism maps and precipitation maps for it, and we targeted certain regions to design our test matrix. Then we went and performed some of these SSM tests, dynamically increasing load over a period of time, really short-term tests, less than 100 hours. And then using our well-posed model, we were able to predict conventional creep curves out to over 1,000 hours. I think it was actually out to about 4,000 hours is what we were able to predict. So this really saves a ton of time. A number of tests less than 100 hours gets out to all the way out to 4,000. And it's compared to conventional CCT, conventional creep tests. So this was a really positive result for us. Next slide. From there, we thought, well, how can we speed this up? And how can we also use a process where we have a material that we don't have those mechanism maps for? What if we're making some new crazy powder where we don't have these maps? What kind of test could we use to make decisions about AM materials, new materials development? For that, we developed the dynamic negative step test, where instead of stepping up the load and having these very fixed hold periods, we dynamically step down the load and we closely track and dynamically adjust these hold periods to keep the material on the edge of instability. Basically, we create a test that tortures the material until it fails. And it tortures it across a number of mechanisms, different load levels that can transition through real mechanisms that can exist in that material. And from this torture test, it gives us an ability to compare, a comparative ability between AM parts that may have different build orientations, process parameters, maybe different powder chemistry. But what's also advantage is that this test is even faster. This test accelerates at a higher rate. But the disadvantage is that we're not really nucleating phases that we would expect because we don't know what phases might nucleate. Next slide. So for this study, we went ahead and studied AM material, electron beam melted Ti-64. We did these DNST experiments, dynamically decreasing load. And we studied samples that were printed in different build orientations. Analyzing the experiments, we came up with metrics, things like rupture time, minimum creep rate, ductility, as well as strain energy dissipation, energy-based term. to make decisions, to make accept, reject decisions about which orientation is best. But also using well-posed models, again, we're able to predict the conventional response of any of these different build orientations. Here we see our model predictions for the vertical direction, which we found was the best performing direction. And we're predicting out to, looks about like 8,000 hours of life. And look, our experiment was less than 125 hours. So this is a very incredible tool in your wheelhouse. It allows you to screen a material based on processing parameters, and it allows you to kind of predict its full-scale performance in a really narrow period of time. Next slide. So there are other things in rapid testing that we're also interested in doing, but now let's switch over to parallel. So let's click once. So we're going to go parallel, right? So we got to have it parallel, and then we're going to test all at once. So let's click one more time. So we're going to move down. We're going to do these tests in parallel. So another really interesting demonstrator that we are working on in my group is this idea of gradient boundary condition testing. To be able to test a material in parallel, to get more than one curve of data out of a single sample. Two concepts that we've proposed is this idea of the delta sigma and the delta t test. In the delta sigma test, you have a geometry that's non-uniform, so that when you test that sample and you pick points along that geometry, each point has a different value of stress. If load is constant, as you change the cross-section, stress changes. And if you carefully contour that shape, you can minimize triaxial stresses that could develop, right? You can also minimize how much stress concentration you have. Now, if you use digital image correlation, which is able to track the strains on the surface of a part, then you're able to extract creep curves, an infinite number of creep curves along the profile of that sample. So from one sample, one test, you get one sample, an infinite number of tests, depending on how much focusing optics you have, right? Depending on how much zoom you got on your camera. Now, in the delta T test, you have a uniform sample, so you have a constant stress, but you adjust the temperature gradient. So you adjust the temperature field around that sample. And then if you have an infrared camera and you have your DIC optical cameras, you're able to measure temperature along that profile. And each of those points at different temperatures, again, represent a different curve, a different test. Stress and temperature gives you a different curve in different combinations. Next slide. And I think this one, okay, there we go. So this is what you end up with. If you have a symmetric boundary condition, you can get replicate testing, like if you have a symmetric boundary condition. So like sigma min, you see we have two curves there because there's 2 points at minimum stress, right? And so from one sample, you literally get as many curves as you want. The dotted line means as many as you are able to get through your optics, right? As many individual strain gauges along that sample that you can pull. Next slide. So in this new lab that I'm building, we've been developing a test setup to do exactly these experiments. So we've got an MTS machine here set up with a resistance furnace, a 3-zone resistance furnace, goes up to 1400 degrees Celsius. And then we also have an optical viewport that allows us to actually see the sample when we're testing. So we have a delta sigma specimen design that has a very slight radius, right? Very slight radius along it that will give us a range of stresses of about 100 megapascals. It's kind of surprising. And then also, because our furnace is a 3-zone furnace, if we have a uniform sample, we can adjust the zones independently to create a temperature gradient. Next slide. Now, we could even take this a step further. Instead of doing delta sigma and delta t independently, we could also combine those together, where we have a sample with a gradient shape, We have a gradient temperature field, and now that enables us to do tests that are more like service-like conditions, where depending on how we design where these gradients are, we can literally have a test that has multiple worst-case scenarios for our actual performance part. And then if we want to get even crazier, we can use some of those rapid techniques, dynamically changing the force, the load, or even dynamically adjusting the temperature field, moving it up or down to accelerate the capture of data from these types of samples. Next slide. And we have another setup in my lab that we're building. It's not fully integrated yet, but it includes another MTS machine with hydraulic grips that are water cooled. It includes an induction heater system that's mounted behind on a gantry system. And then we also have built this summer a gantry system for our optics. So we're able to put multiple cameras, DIC, optical cameras, infrared cameras, and then allow us to move forward or backwards to get fully in focus, to get as much information we can out of a sample. Let's click, and then click one more. Now, another concept that we're working on, we're building a demonstrator with the CDME, the AM center here at OSU, is this idea of gradient materials. And you can go ahead and click, David, maybe once or twice. So the idea of gradient materials is instead of printing one sample that is of one processing parameter conditions or one type of powder, what if instead we built vertically up or along the build plate a sample that has combinations of different powders or processing parameters or even build environments, and built up a single sample that has multiple distinct regions that we can study. If we then take that sample and do DIC on it, and if we have fiducial marks that tell us the different distinct regions, we can then, from a single sample, extract information like the tensile properties or the modulus, or even creep curves, or even probably not fatigue, but at least creep properties from multiple materials from a single sample. Now, that really could be helpful in MGI, in finding in new materials discovery, or in trying to figure out good processing parameters, trying to finely tune process parameters for high temperature applications. Next slide. Now, the final crazy idea is, well, what if we just wrap everything together? If we have parallelized material, so we have a multi-material print, gradient material, we have a gradient temperature field, and we have a non-uniform geometry, so we got gradient stress. Well, such a sample as that could be a great sample for A-B material comparison, where maybe we have two candidate materials. We want to put them in service. We don't know which to go with. Well, we could design this very specialized test to help us make a decision on which material is best for our specific performance requirements. Next slide. And so finally, we move to miniature. And unfortunately, we don't have time to cover miniature, right? But there are a lot of things that we can do in miniaturized testing that I'd love to talk with you offline. So that's all I got. Click once or twice.
Okay, great. Great job, Calvin. Thank you. Just a couple quick closing thoughts here. So thank you, David. Thank you, Calvin. Appreciate your energy and presentations and your time this afternoon. To me, the sort of way I contextualize all this is we're going to need both categories of testing that we talked about. The chemistry is critically important, the feedstock characteristics, the mechanical testing and screening of the materials at that length scale. And then maybe the other piece that we didn't talk about here, but somebody asked in the Q&A about looking at additive components or new materials, I think is also the NDT. So the in-process monitoring, the NDT at the part scale, all those three buckets together are really, really important. And I think what's really exciting and we're exploring as a community of practice, Calvin mentioned it a few times, is AI and how we can leverage AI and machine learning with some of the new tools that are out there. Particularly, I'm personally interested in image analysis, so happy there are folks that have questions on that. So we'll open the floor for questions. The first question, I'll just read it in case I didn't cover it or we didn't cover it. New materials for additive are being developed all the time. What is the approach for testing a material that has never been seen before? So I think the question was popped in the middle. Calvin, maybe I'll let you sort of address that briefly, and then David, if there are a few high points, and then we've got another question just came in. Go ahead, please.
Yeah, I mean, that's really the challenge. In new materials discovery, people are developing new powders. People are developing powders that are coated in oxides to try to create ODS alloys. I know the folks at NASA are doing that. And so it is a challenge. What I've seen a lot is people start with a line scan. Can we just find process parameters and create a line? Can we get grains to form of a reasonable size? Then people move and they create a cube. Can we make a cube? Can we build up? Can we get some Z on this? And then from there, people start printing coupons. And every step in this process is continuous optimization of these process parameters. And for me, I'm a high temperature guy. I want this to go in a jet engine. I want this to be a rocket engine. I don't want room temperature properties. So I've leaned into, can we just go straight to my part? Can we just go to high temperature? And the DNST test is a test that's for that. It's a test where we don't know much about the material. Maybe we just know its yield strength and tensile property. We just did a tension bar test. And we don't know deformation mechanisms. We don't know what phases will nucleate in 5 years. But can we do a test that screens and gives us confidence that this material should be something we go do those long conventional tests on? So that's what I'm kind of leaning into. There's standardized testing. And then I say, let's do the screening tests. Let's develop these screening tests. Let's get signatures of acceptance, rejection.
Yeah, and I think that all excellent points, Calvin. But there's another side of things, especially from the qualification standpoint. When you're trying to qualify a new material, right? Let's say we've got some screening tests done, and we've done the development part, and we're ready to qualify. The nice part about materials engineering at this time is rarely, a little asterisk there, do we find a material that is just never even, no one's ever come close to it before, right? We're usually incrementally improving upon previously developed materials. And so we can base our qualification and the testing that we suggest or that we do for qualification based on those previous alloys that are in the same family or for the same purpose. And that's where we can start our qualification testing. And whether we decide to change it for various reasons, that's usually backed by development ideas, right? The researchers say this is a novel alloy, it needs to be tested in a certain way to show off what it really has to show. And then we'll work with that. But conventionally, you're not reinventing the wheel every time, you're just putting it on a new track to see if it works as well.
Great, thanks both of you. We have another question in the chat. Austin asks, powder feedstock cleaning and switching in a machine can be intensive, and how? Are current machines viable for the idea of layering multi-materials in one build? So maybe I'll make a comment or two on that and then invite my co-panelists. And Jason, I should have checked, are the attendees able to speak, or do they need to stick to the chat, or can they raise hands and chime in, or how are we set up today?
No, attendees are all muted when they come in, so they'll just have to stick to the chat. Yeah, if you have questions, please get them in the chat.
Yeah, and okay, great. So, I mean, I would answer the question and sort of, I'll stick to powder for the moment, in two parts, right? So, multi-layered functionally gradient materials using the blown powder techniques have been attempted for a long time. They keep getting better and better as the integration of multi-powder hoppers and different systems have improved over time. So my view is that's sort of an integration challenge. And I think that's true also on the laser powder bed fusion side. There have been a few commercial companies over the years that have demonstrated this. And there are some research groups, including some collaborators, longtime collaborators of mine at the University of Louisville, also the CME folks at OSU that Calvin referenced have attempted some of these things. So I would say it's somewhere like mid TRL, MRL. We can do it in a lab. And then the question is, can we really do it for a part? So Calvin, I really liked how you framed it to use it for testing, screening, materials discovery. I would say that's an area that as a community, it's recognized that we can use it for. I actually haven't seen a full scale, all printed additive part out in the wild that has that yet. Right? I mean, we use these techniques to repair things like turbine blade tips and bliss and things. But as far as the full additive parts, yeah, I haven't seen one in production yet. I don't know, David, Calvin, do you have anything to add?
Yeah, so yeah, we're attempting it at CDME with a trunk DED system. They've had some work in the past, trying to I think it's Inconel 718 and 316 stainless. You need a compatible material in order to do multi-metal. I've also seen some really great work using the Form L2 DED machine that has very fine control. You can really, I've seen specimen made similar to kind of my sketch there that look really good. I think it's the future, it's a future concept, making these multi-metal parts. I think it's possible. It's going to take development, improvement of machines. Current machines may not be viable for that blade that I envision, but it's a part of the future. It's coming.
Mm-hmm.
Yeah, I just to agree with everybody. Blown powder definitely is more capable, easier to just change the hoses over. Other techniques that I've seen in the industries or academic spaces is to print something in one machine and physically take the build plate out and move it to another machine and start the powder bed process all over again with your old part as the build plate. Obviously, you don't want to do that for more than a couple of iterations, but it's one way to use the older style laser powder bed fusion machines that aren't integrated with dual hoppers or something like that.
Mm-hmm. Yeah, great question. Any other questions? Anybody? We probably have time for one more. If anybody wants to drop one in the chat. If not, again, thank you so much for your time this afternoon and the opportunity for the three of us to share our passion for materials testing and development. Thank you, America Makes, and Jason, for the opportunity. I'll let you share any closing logistics or anything, Jason, that you've got.
All right. Thanks, guys. That was a wonderful, wonderful presentation. Really enjoyed it. Thank you. So yeah, I guess that's going to wrap up today's TRX webinar series. I'd like to thank Ed, David, and Calvin once again. Like I said, great presentation. Thank you very much. If you have further questions, you can reach out to them directly here. They have their contact information on the screen. So make sure to do that if you want to follow up. And there should be a post-webinar survey going out to all of you who participated today. We really appreciate the time that you take to provide us feedback so that we can continue to improve and strengthen the additive community. And once again, if you'd be interested in sharing the TRX webinar series, you can reach out to me, jason.thomas@ncdmm.org, or you can go to our website and fill out the form to request a webinar. So once again, thanks everyone, and thanks, Ed, David, and Calvin. Have a great day.
Bye, everyone.
Thank
Thank you.
See ya.